Hey guys, I'm going to show you now an example of a conservation of momentum problem. I went over this in class, but some people were absent and I just kind of had to go through it a little bit fast and some people were a little bit confused on it. Okay, so this is the setup. We have in this example, a 6 kilogram cart going at 10 meters per second to the right, and it's going to run into a 2 kilogram cart that's going at 20 meters per second the opposite direction. And it's going to be an elastic collision, so they're going to bounce off of each other. And what we want to figure out is the speed of both of the objects after the collision. Now, if you think about it, in the real world, they can only do one thing, so it should be predictable. Now, in the past, the way we've seen these problems is we've always given a setup like this, and then we said, and after the collision, this one is going at such and such a speed in this direction. What's the other one? And those are much easier. It's a straight elastic collision conservation of momentum problem. Now, this one obviously is one level higher. AP is not going to ask you this question. However, it is something that you need to know for college, and you will be expected to be able to do it if you take a college physics class. And part of my responsibility is to get ready for college as well. So I am going to show you how to do this. Now, on the test that's coming up on Friday, I'm going to have one question like this, but it's going to be extra credit only. Okay, because again, you're not going to see something like this on the AP exam. So if you can do it, awesome. So I'm going to show you two ways to do it. One is quite math intensive, and a lot of people consider it a huge pain in the neck. I'm one of those people. And then I'm going to show you a shortcut way that's much more visual, and it'll make you look like a genius if you can figure it out when you're going to college. The problem with it is very visual. And some people, it just doesn't click for. And what I call the hard way, they find it easier, the purely mathematical approach. So I'm going to show you both with the easy way first, and then I'll show you the hard way at the end. Anyway, so let's get to it here. I'm going to reduce this a little bit, and I'm going to start by showing you our air track simulators that we had before. So I have this one set up for an inelastic collision. So they're going to stick together, and I have the red mass of 30 going at a speed of 40, and the blue mass a speed of mass of 40 going at a speed of negative 30. So we have some symmetry here. Mass of 30 going speed 40, mass of 40 going speed 30 in the opposite direction. They're going to hit and stick. And what I would like you to do is pause the video here and predict what will be the speed in this inelastic collision. When the two things come together and hit, are they going to drift off to the left or are they going to go to the right? So yeah, pause it, take a quick look. You may be able to just do it intuitively, but if not, then pause it and do the math. Anyway, so here we go. I'm going to hit play, and here they come together. Drum roll, and they stop. And this shouldn't be too surprising because the momentums for each of them is the same. 30 times 40 is 1,200. So this has a positive 1,200 unit momentum. This has a negative 1,200 unit momentum, which means same momentum. When they hit and collide, they're going to cancel each other out, and the momentum of the whole system is 0, so the thing just sits there. Okay, now let's make it slightly more complicated. What if it's an elastic collision? It's the same setup, but what is what will the speed of the two things be when they bounce off? And this is really the question that we have today, so I don't want you to try to figure this one out. Just think about it, make a guess, and we'll see what it is. Here they come. And they bounce, and notice that they have the same speed just in the opposite direction. So the red one was going 40 to the right. It collided and went back at the same speed in the opposite direction. And the blue one had a speed of 30 to the left. It bounced off and it had 30 to the right. So we wind up with a symmetrical situation here. And when you think about it, this kind of makes sense because in a elastic collision, the momentum has to be conserved, which means there has to be just as much momentum going out to the right as came in from the left, and vice versa. So since 1,200 units came in from the left before the collision, 1,200 units has to go out to the right. And since the masses are what they are, the speeds have to stay the same too. So the result is that they bounce out at the same speed that they came in. Okay? Now, you may need to reflect on that a little bit to see that that's the case, but I could have chosen any numbers here, and as long as the momentum in each direction was the same, the speeds going out will be the same as the speeds going in. You can even open up the simulator if you want and play with it to see if that's true. But I think if you think about it, you'll see that does actually make sense. Now, we are going to take advantage of that fact in the shortcut method. The fact that when the center of mass of the system is not moving, which it is in this inelastic collision scenario here. Let's make that go away. There we go. The center of mass of this system was not moving. Even when the two carts, the red cart and the blue cart, were coming in and they were each carrying momentum, the center of mass of the system was not moving. And we see that when we do an inelastic collision and have it stick there. And as I said, we're going to take advantage of that fact. When the center of mass is not moving, then the speeds in to the collision are the same as the speeds out of the collision, just in the opposite direction. Okay, let me switch over here to the clipboard so we can do the math and see how this works. Okay, we'll open this up. And all right, so here we are. 6 kilograms at 10 meters per second, 20 meters per second going the opposite direction on 2 kilograms of mass. Now, this is not a symmetrical situation, so we are not going to have something where it just sticks or where it just bounces off and goes out at the same speed. We have to do a little more manipulation with it. So what we're going to do is we're going to first calculate the speed of the center of mass. So we want to know actually the velocity of the center of mass. That's going to be our first step. So this has a momentum of 60 in that direction. This has a momentum of 40 in that direction. When we add them together, we find that the total momentum is 20 in that direction, and the mass is 8 on 8 kilograms. So that means that the speed of the center of mass is going to be 20 divided by 8, 20 divided by 8, which is equal 2.5 meters per second, and it's going to be moving to the right because this momentum dominates over this one. Okay? So this is just, I went through it kind of fast. This is exactly the same as the inelastic collision calculations that we did during the air track simulation. Okay, I probably should write that here. So we have M1 V1 plus M2 V2 is equal to M1 plus M2. In other words, the total mass times the final speed. This is M1 V1 plus M2 V2. This is the total momentum. That's this side. This is the total mass. So we're going to divide the total momentum 20 by the total mass 8, and we get a speed of 2.5 meters per second to the right. Okay, so we're going to keep track of that. So the center of mass is going 2.5 meters per second to the right. Now, the second step is we're going to figure out how fast our carts are going relative to the center of mass. Because remember, all speed is relative. And if we use our center of mass as our reference, we can figure out how fast they're moving relative to that. So the 6 kilogram one was going 10 meters per second. So this is the 6 kilogram column. This is going to be the 2 kilogram column over here. Now, the 10 meters per second is trying to catch up to the center of mass. So its speed relative to the center of mass is going to be slower than its speed relative to the ground. So we're going to subtract 2.5 from 10. So 10 minus 2.5, and we get 7.5 meters per second that way. This is the speed of the 6 kilogram cart relative to the center of mass. Okay? Now, the 2 kilogram mass is meeting the center of mass head on. They're going opposite directions, so their relative speed is going to be greater. So that is going to be 20 meters per second that way, plus 2.5 meters per second that way. Really just we're doing absolute values here, 20 plus 2.5. Anyway, so the relative speed is 22.5 meters per second, and it's moving toward it. Okay? So these are the speeds relative to the center of mass. That's what that column was. Okay, now we're going to use that thing that we saw on the simulator where the speed in is going to be the same as the speed out after they collide and bounce away. So the speed of the 6 kilogram mass is going to be 7.5 meters per second, going away from the center of mass this time. And likewise, for the 2 kilogram mass, it's going to be 22.5 meters per second away from the center of mass. That's the second step. So that is make them bounce. Step 1, step 2. Now, step 3 is we need to find our new velocities relative to the ground. So we need to kind of subtract out the speed of the center of mass to figure out how fast these things are going relative to the ground now that they've bounced. So we need speed relative to Earth. Okay, now these are going away from each other. The 6 kilogram block is moving away from the 2.5 meters per second, but the 2.5 meters per second is itself dragging over the ground. Okay, so this is kind of trying to go backwards because it's relative to something which is moving to the right. So that means that the speed relative to the ground is going to be slower than this. So we're going to subtract the 2.5 and get 5 meters per second that way relative to the ground for the 6 kilogram block. And this one is moving away from something which itself is moving to the right. So these we're going to add together, and we're going to get 25 meters per second to the right is the speed for this one relative to the ground. Okay? So to catch up to where we are, we do a calculation to find the velocity of the center of mass, and that's just the straight inelastic collision calculation that we've done all the time. Then we figure out the speed of our two carts relative to the center of mass. Then we reverse those because when they bounce, they go out at the same speed relative to the center of mass that they came in. And then finally, for the last step, we find the speed of our objects relative to the ground. So we have to subtract out the speed of the center of mass. And that's it. This is actually the answer. So the speed of the 6 kilogram block, it comes in at 10 meters per second, bounces out at 5 meters per second. The 2 kilogram block comes in at negative 20 meters per second and bounces out at 25 meters per second. And I really should put negative 5 on here, but I mean it goes to the left. Okay, now that's the quote unquote easy way. That's the easy way. All right, now how's the hard way work? Well, there's one more piece of information, maybe two more pieces of information that you have to have. Let's just to kind of ignore this for a moment here. Okay. First of all, in a truly elastic collision, it's not just momentum that is conserved. We also conserve with something called kinetic energy, which you may have heard of, maybe not. And we haven't talked about kinetic energy yet. We're going to do that in the next unit. But there's a formula for kinetic energy, and this is it. The kinetic energy of a moving object is equal to 1/2 the mass of that object times its velocity squared. That's the formula. Just take my word for it right now. Like I say, we'll learn about this more later. So that's, so in an elastic collision, momentum is conserved and kinetic energy is conserved, both of them. All right? So that means that to solve this, this problem, we have to do an equation where we note that the momentum is conserved. So this is the momentum of the 6 kilogram block before the collision and the 2 kilogram block before the collision. And we set that equal to the momentum of the 6 kilogram block plus the 2 kilogram block after the collision, but we don't know the speeds. So this is the momentum of the first, 6 times whatever the final speed is. This is the momentum of the second, 2 times whatever the final speed is. right? Um, and that is a true statement. And we're going to boil this down to put one of those variables in terms of the other. So you can follow through when you see it. And we get V2 is equal to this. So we have V2 in terms of V1. All right, the other part of this is we do the same thing for kinetic energy. So this is the kinetic energy of the 6 kilogram block before the collision. This is the kinetic energy of the 2 kilogram block before the collision. And that also has to be conserved. So we set that equal to the kinetic energy of the 6 kilogram block after the collision and the kinetic energy of the 2 kilogram block after the collision. But again, we don't know the speed of either one. We just have to call them V1 and V2. However, once we have this term, then we can substitute in our V2 term. That's what I've done right here, and then start boiling it down. Now, when it boils down, we get a quadratic formula, a quadratic equation rather, and then we use our quadratic formula, yay. And when we work it all out, we wind up with two answers, as you know, two answers for V1. As you know, the quadratic formula always yields two answers. This one, it comes down to either 10 for V1 or -5 for V1. Now, when we plug our 10 back into our term for V2, we find out that when V1 is 10, V2 is -20. Well, that's our initial conditions, okay? Which is actually kind of a nice check to make sure that we're on the right track, because one of the solutions to this problem is the initial state, so yay. And then the other one comes out to be -5 for V1 and +25 for V2. And that's what we got. So it works. Anyway, you can look at this to your heart's content at your leisure. I guess I should push this up a little bit so we can see the whole thing. Let's see. There we go. Yeah, so that's the quadratic formula once you get to it. All right, anyway, there you go. As I said, there's going to be an extra credit problem on the next test to have you solve a problem like this. Use whichever method you choose to. It is extra credit. It will not affect your grade. All it can do is make your grade better. It will not skew the curve, okay? So this is here for you if you have the time and you have the interest, but I promise you it's something you'll need to know in college physics. So here you get a head start on it. All right, well, thank you for your time, and we will see you next time.